In the previous part, we talked about linear impulse and linear momentum. Here, I'm going to extend it to angular impulse and angular momentum. What's the meaning of that? Let's say we have a particle which is moving in one direction with the velocity of v, and let's say the mass of this particle is m. The definition of angular momentum is this. We need to define it about a point. So the angular momentum of this particle, which is moving with the velocity of v about point O, is going to be equal to r cross mv. It is very similar to the moment that you had in statics. And we show it with h. So angular momentum about point O, we show it with HO, is going to be equal to R cross MV, or R cross G, the linear momentum. So it is very similar to the moment of a force about a point. So if I had a force like F here in the direction of this velocity, then the moment of that force about O is R cross F, if you remember it from statics course. We are going to have exactly the same definition for angular momentum. So this is angular momentum of this mass about point O, which is a pure definition, right? And it's going to have one interesting concept behind it, which I'm going to derive it for you first, and we are going to see how it is useful. So this is the linear momentum, and if I take a derivative of it with respect to time, I'm going to have d dt of HO is going to be equal to derivative of the other part. But in the other part, I have R and V, both of them are changing. So I need to use chain rule and take derivative of both of them. Derivative of R with respect to time is velocity. So I'm going to have velocity cross product mv plus R cross derivative of mv with respect to time. So I'm going to have R cross product to m times derivative of the velocity, which is acceleration. The first part is v cross mv. Both of these vectors are parallel, right? So these two vectors are parallel, so the cross product of them is going to be equal to 0. The other side, or the other part, I can replace mass times acceleration with some of the forces. Based on Newton equation, some of the forces that we have on this particle is going to be equal to mass times acceleration of the particle. So it's going to be r cross sum of the forces that we have on the particle. And r cross force is the moment. So the moment of all the forces that we have on the particle about point O is going to be this. So I can replace it with sum of the moments about point O. So again, this is the moment of all the forces that we have on this particle. We need to take a moment of them about point O. So the derivative of H is going to be sum of the moments about point O. And we can do exactly what we did for linear momentum. I can multiply dt to this side, then integrate both sides. So what I'm going to have dHO is equal to sum of the moments about point O dt. What I did, I just multiplied dt to the other side. Now again, like the previous one, let's say this mass is moving from point 1, goes to another point, like point 2. So this is the starting point and this is the end point. And I'm going to integrate between these 2 points. So from 1 to 2, and integral of the other side from 1 to 2. So integral of dH is just HO. From 1 to 2 is going to be HO2 minus HO1. HO2 means angular momentum of the this mass or the system about point O at point 2. And HO1 means angular momentum of the mass or the system in the first condition, right? It's going to be equal to the other side, which we have sum of the moments about point O dt, and let's say at the first point time is equal to 0, and at the end time is equal to t. So we are going to have this equation, which is pretty similar to the equation that we had for linear momentum. In that equation, we had g2 minus g1 is equal to integral from 0 to t, sum of the forces dt. So we have very similar thing for the angular momentum. This integral is called angular impulse. Sometimes we know the moment as a function of time, which you can see it in the problems of the book. So if I know the sum of the moments that we have on the system as a function of time, I can put it here and integrate it and see how the angular momentum is changing between 1 and 2. Sometimes in some problems, we know some of the moments about a particular point like O is equal to 0. In that case, this integral is going to be equal to 0, and we are going to have conservation of linear angular momentum. HO2 minus HO1 is going to be equal to 0. So we are going to have conservation of angular momentum. Or HO2 is equal to HO1, which we are going to see some of examples for this case.